Hello, this video will be to help you correctly answer problem number 32 in chapter 2. Like always, we'll start with a graph. This problem definitely needs a graph, just like problem number 7 on the homework. So, first thing you need to understand is what's happening. So, we have a car, okay, and the person is trying to determine if they should speed up or slow down as they approach a yellow light. So there's my car, and I'm gonna have an old-fashioned. Well, here, let me join the road first. I'm gonna have an old-fashioned light signal, and again, you are not graded on how well you draw. I just like to put in a little bit of flair sometimes. So this is my old-fashioned light signal. Okay, and the problem, so this is a curb. The problem is there is an intersection, as you would expect at a light, and there's traffic in the opposite direction. So the person's trying to decide whether or not they should stop or just speed on through, which in general, hopefully you guys know you should typically stop. Uh, if you're that far away where you're not sure if you're going to make it, then you should be close enough to, or you should be far enough away to stop in time. Okay? First thing, you want to label what you know. So we need to decide a reference. I'm going to say where the car starts is my reference frame. So X initial here, 0 meters. They tell us that the light is 28 meters away. Again, I like to use letters, so I used an L for light, but I know a lot of you guys like to use the numbers, so we're going to do X1 here is 28 meters. And you also need to know the position of the end of the intersection, because the person's car needs to get to that point before the light changes for the other direction, and they tell you that that position is 15 meters from the 28 meter mark. So that means that x2 is actually 43 meters from our reference frame. Now this would be a good time to go ahead and put in a positive symbol. So I say to the left is positive, which means we're going to have a positive 43 and a positive 28. The velocity that the car starts with in the x direction is a positive 45 kilometers per hour. And this problem is odd because it actually has two different accelerations. You have an acceleration for when the person is slowing down. Okay, a deceleration is still an acceleration, it's just a negative acceleration. And then you also have an acceleration for if the person speeds up. So we're going to actually need to label both of these. So I'm going to use A for acceleration, but I'm going to use A with a subscript of a D, meaning deceleration, slowing down. Negative 5.8 meters per second squared. Okay? But it could be that acceleration, or you could have an acceleration that's speeding up. You could use AS for speeding up. I used Oh, looks like I used to use a plus sign. I'm going to use AS then. So AS is for speeding up, and you're going to have 20 kilometers per hour in 6 seconds. Now, in case you're wondering where I got the 20 kilometers per hour, they said that the person can speed up from 45 kilometers per hour to 65 kilometers per hour in 6 seconds. Well, that's a change in velocity of 20 kilometers per hour. So you're already starting from 45, so we know that's the scenario we're looking at. So you're going to go ahead and write 20 kilometers per hour in 6 seconds, and that's positive. That's all you know. Okay, that's actually all you need to know as well. But once you've done this, you need to go back and find the standard units for the variables. So we'll go ahead and convert the velocity first. So we're going to have the velocity initially is going to be a positive 45,000 kilometers per hour. And just to help you guys follow along, this, let me make that a little thicker. There you go. This is being done here to be able to get the correct units. Okay. In case you didn't watch the other video, like you didn't need help with that one, I write it over so that it makes it easier to do the conversion. Okay, so now I write an hour on top, and the time I need it to be in is going to be, wait a minute, I made a mistake. It's not 45,000 kilometers. I jumped ahead there. Sorry about that. You will actually need 45 kilometers per hour. I jumped a step. That's going to be the same as 45,000 meters. I'll keep that in the video because it's a good example of paying attention to what you're doing. So this matches 45,000 meters is the same as 45 kilometers, and we have to change this hours. Okay, we have to get that to seconds. So we'll do an hour over, and we know we want seconds, but what you have to decide is how many seconds are in an hour. You don't really need to decide, you need to measure it. So 60 minutes in an hour, 60 seconds in a minute, so 60 times 60 is going to be 3,600. Okay, so you have 60 times 60 gives you 3,600. That number should be memorized, okay, because you're going to use it a lot. If you watch the other video, you've already heard me say that, but I know some people came in for help with the first problem, so they may not have watched the first video. When you do 45,000 divided by 3,600 seconds, you get a velocity of 12.5 meters per second. So all of this was just to get to that initial x velocity. Now there's something else that I didn't write in the list because it's not needed for both scenarios, it's only needed for one scenario, and that is the time. So we're actually going to write it above the acceleration for speeding up. T equals 2 seconds. But write in parentheses that it's the time for the light to turn red. Because that will help you remember that that time does not matter unless you're trying to push through it. Oh, it looks like I deleted the U. Okay, that does not look good. Turn. Okay. Now there's two ways you can do this problem. You can figure out all the values in the standard units and then solve it, which is what I would recommend. Or you could say, I want to answer if she can stop in time first and then see if she can speed up. Okay, but I'm going to show you how to convert everything first, and then you can determine if you're going to have the scenario work for stopping or for speeding up. So we're going to change the color here. We'll first look at slowing down when we're converting. In this case, I would actually make a table like this. So this is for question part A for stopping. You're explaining that A is going to be the scenario for stopping. But you're making a table so that you can actually write the values that are special for stopping, and then for B, that's speeding up. Now, stopping, the final velocity, okay, Vx final is 0 meters per second, because that's the definition of a stop. And we already had AD for deceleration was negative 5.8 meters per second squared. So we didn't need to do any conversions there. Basically what we did is just make sure we organized it so we knew where the stopping values are. Now for the speeding up values, your velocity is different. So velocity final in this case, they're telling you that 65 kilometers per hour is that maximum velocity. So you'll go ahead and write 65 kilometers over an hour. That's the same as writing 65,000 meters. You have 1 hour on the bottom, take an hour on the top, divide it by 3,600 seconds, you'll get meters per second. Okay, don't forget that 65 is positive because you're still going past the light zooming. Okay, so you're going to get positive 18.06 meters per second for that final velocity. The acceleration was told at positive 20 kilometers per hour over 6 seconds. So this one can be a little trickier to convert. Okay, I'm actually going to rewrite it a different way first. I would rewrite it as 20 kilometers per hour. Okay, where you can go ahead and think about how you would convert that. So actually, let's take out the kilometers. Let's go ahead and write it as 20,000 meters per hour. And we can go ahead and multiply that by 1 hour over 3,600 seconds. And then multiply that by 1 over 6 seconds. Now this 1 over 6 seconds comes from this right here. Okay, so the middle section was the conversion like normal, and then I add an additional 6 on the bottom from what was already given in the value. Now that would be 20,000 divided by 3,600 times 6. Okay, remember you have to multiply the 3,600 by 6. When you divide, it's not multiplying the other section. Okay, so the bottom is multiplied and then you divide the top. You get a positive 0.926 meters per second squared. And that concludes all the values you need. Okay, now I'm going to show you how to solve for part A. I'm going to zoom out so we can continue to see everything. And we need to identify an equation that will determine the distance the person can stop. When you look at the equations, it's important to keep in mind we do not have a time for the first scenario, okay? Because if the person stops before the light, it doesn't matter if the person stops after the light turned red because the person never crossed the light. So the equation that doesn't use time is the third equation. So we're going to go ahead and write that. Just write it the way it says on the equation form. So you're going to have v, why is it doing that? V, okay, vx squared equals vx initial squared plus 2. Now we're going to stop here. It says 2ax on your equation sheet. Okay, what I want you to do is write a d, because we know we're talking about the deceleration, so it's okay to use that now. Then you have x, and the final in this case is what we're trying to measure. So we're not going to write x1, we're just going to write x minus x initial. Okay, so we have all the values there that we need, and the x is what we're trying to solve for. So we need to isolate for x. You're going to do that by subtracting the velocity over to the left and dividing by 2AD. To make it a little bit easier for you, we can identify which ones are 0. So we could also just say, okay, this is 0, so I don't need that. And V final is 0. So when we subtract, we'll have, let me show you, we're going to subtract this over. Okay, and then we'll divide by 2AD. So we do that afterwards. So once you do that, you're going to have x equals a negative vx initial squared, all divided by 2AD. And again, AD was just your deceleration. Okay, the acceleration of it slowing down. For example, I shouldn't have written the d so large. This a should be bigger when I was dividing it, and the d should be a subscript. Okay. So really all you're doing is plugging in two values. Okay. You have the initial velocity. So in this case, you have x equals a negative, because you cannot forget about that minus sign that was in front of the term, but it's not a negative squared. Okay, you're squaring it, and then you have a minus sign on the outside. So when you plug in that value for the velocity, that positive 12.5 meters per second squared, you're going to end up with a negative on the outside. Okay, and then you have 2 on the bottom, and the deceleration was negative 5.8 meters per second squared. Now this is where the negatives become important, because you have a negative on the acceleration, but you have a negative on top, so those negatives will cancel out and give you a positive displacement, which makes sense because the car is not going backwards. Okay, so x will be a positive 13.5 meters, which you would round to 14 because you only need 2 sig figs in this case. So you say x equals a positive 14 meters, and you box that answer. Okay, that's the answer for part A. That means that she would definitely, or the person would definitely stop in enough time. Okay, it only takes half the distance that the person has to stop. Now, some people would say, okay, well, if the person can stop, I don't need to calculate if they'll speed up past. There's some logic to that, but in addition, you might be able to have both work. So you could explain that both options are viable, but you might then choose one answer is better than the other. Okay, hopefully you would pick that stopping is better than trying to speed up past the intersection. But we really don't know if speeding up will work yet unless we show it with an equation. So I'm going to scroll down, and so we're going to do part B now. Now, with part B, you have the time that the light takes to turn red as a limitation. So your equation that you use has to involve time, but it also has to include a position, which means that you cannot use the first equation. You have to use the second equation. And on the equation sheet, second equation reads as x equals x initial plus Vx initial multiplied by time plus 1/2, and it says acceleration and the x. Now in this case, the acceleration is the speeding acceleration, so just write a with a subscript of an s, and then you have t squared. Okay, now that's the equation that we have to work with. Keep in mind that the position that you start with is 0. That's your reference, so we can take that out. Time is not 0, acceleration is not 0, and the velocity is not 0, so it's the only thing you can take out is the initial position. But the other nice thing about this equation is already isolated for what you need, so you can actually just plug the values in now. So you're going to have x is going to equal the initial velocity in the x direction, which was that positive 12.5 meters per second. And then the time is 2 seconds. Then you add in the 1/2. The acceleration is a positive 9 point, oh sorry, not 9 point, 0.926 meters per second squared. And then again, you're going to have the time of 2 seconds. Now, at this point, you might be wondering, why do we use the 12.5 meters per second and not the 18.0 meters per second, 18.06 meters per second that we said for the final velocity? Now, the trick to that final velocity that they're giving us, it takes 6 seconds just to get to that point. So we know it's not going to get to that velocity before the light turns red. Okay, so it's an extra piece of information. Technically, you wouldn't need to write it down. If you missed it, that would be okay. But it was a good example of giving you more practice for conversions. So I went ahead and showed it to you. But if you chose not to include it, that's okay. It's not needed because it technically doesn't get to that velocity in the 2 seconds. Now going back to the equation here, we use the values that we used before for the velocity for both situations. The main difference here is the acceleration is different because you're speeding up, and the time, the 2 seconds, is the real key because it tells you how long you have to get to your destination before that light turns red and you have the likelihood of getting in an accident. When you go ahead and compute this, you get x to equal 26.9 meters. Now this is significantly less than the 43 meters you need, but I also want to make the point that let's say you only needed to go 27 meters. Okay, let's say the 27 meters was the cutoff. It would not be a good idea to round up the answer because that would be acting as though you will make it when you won't actually make it. You'll miss it by 1/10 of a meter. So when you're rounding, it's okay to round if you're not changing your answer to the question. You're not changing the sentence that you would explain. So by rounding this, you're going to end up still missing the 43 meter mark, so it's totally fine. But let's say rounding it actually influenced whether or not you thought the person would make it, then in that case you would not round. You would just keep the value you had. okay, or you would just round it down. So in this case with sig figs, you would have a position of 20, positive 27, should have wrote positive here, 27 meters. So based on this, you would explain in a sentence, or actually several sentences, that the car should stop. The driver would be able to stop with an extra 14 meters before reaching the intersection, and that the car would end up still traveling at a unsafe velocity before even reaching the intersection. Because keep in mind, this 27 meters tells us that the person speeding up in 2 seconds, they're going to be going over the 65 kilometer, or sorry, the 45 kilometers per hour that they started at. They won't be quite at the 65 kilometers per hour that they could reach in the 6 seconds of acceleration, but that's way too fast to be able to stop. Obviously, we know that it took 14 meters to stop when you're at 45 kilometers per hour. So by speeding up, not only are they not going to make it, but they're going to make the crash even worse. Okay, you would explain that you're able to figure this out knowing the distance from the velocity and the acceleration of stopping without needing time, because it's all about the range. Okay, but time is important when you're speeding up because you're limited by the time it takes for the light to go and turn to red from yellow. Okay, if it wasn't for that time being 2 seconds, if it was even 4 seconds, then you might end up with a different answer. Okay, you might be able to say yes, she can go through, or the driver can go through the intersection. But because it only takes 2 seconds for the light to turn red, the person's not going to be able to go through. And that concludes your answer for this example. It's a little weird because of the two different accelerations, but it's a nice example of trying to figure out an outcome based on the kinematic equations and making the decision based on those outcomes.